Hello my esteemed viewers. In this tutorial, we clearly explain the wedge friction. This tutorial comes as a sequel to tutorial number 3, and I think my respected viewers should recall that this is the 4th tutorial. In earlier 3 tutorials, we discussed the fundamental aspects of friction as a resistive force, and in the second tutorial we discussed about the friction that would develop on horizontal surfaces, and in the third tutorial we discussed about the friction that would develop on inclined surfaces. And this tutorial, the case in point is the wedge friction. Wedges are very simple implements. Wedge which will be of triangular shape or trapezoidal shape. This is potato wedges. Of course, potato wedges have no role to play in our engineering mechanics. But anyway, the shape matters. Okay, in order to explain, in order to bring before the shape of the wedge, this example is presented. And here is the some kind of a wedge that is being inserted, that is being embedded into the high heel slippers, and it is and here exactly the role of wedges come into play. And when we cut a big wood with a wedge shaped hammer, it's going to be apart. It's going to be into 2 pieces, and the 2 pieces will change their direction and they will fall apart. And this is possible with the small amount of force because of the friction that is being developed between the wedge surfaces and the wooden surface. And here a huge weight is held in position with the help of a small wedge over here. And typically speaking, the weight of the wedge doesn't matter. Okay, it is disregarded in the analysis of wedge friction, because it is only the friction that would develop on the surface of the wedge, the supporting surface of the wedge at the interface really matters. And and here is once again there is a lifting of a huge boulder with the help of a wedge action somewhere over here, and this wedge is supported, this particular lever is supported by this fulcrum, and this lady is just putting a small effort in order to lift a huge weight. And there is an effort applied by this person, and there is a lever, there is a load that is being lifted, and this is the fulcrum. This is another kind of wedge, and here exactly the wedge action comes into play. And here the cutting blade of the cake functions like a wedge, and the 2 portions of the cake will be apart with a very less effort. And here the wedge comes into play in gears, and here it is typically triangular shaped, and there will be a smooth rotational effort, and the effort, that is rotation effort, which is being imparted over here, or the rotation effect of this is imparted to this small gear by the virtue of wedge action that happens over here. And here again there is a lifting of a big boulder with the help of the wedge action. Here the person is lifting, and here the entire car is being lifted with the help of the wedge action that comes to play over here at this particular interface. And this is the fulcrum, and this is the crowbar. And therefore, to summarize, a wedge is a piece of metal or wood which is usually triangular or trapezoidal in cross section. Wedges are used to make small adjustments in the alignment of heavy loads and for tightening the keys of the shafts. Wedge may be used alone or in pairs depending on the situation. Weight of wedges is usually neglected because weight of the wedge never come into play. It is exactly the friction that is developed. As I said earlier, due to small angle involved and the available friction, loads are so aligned with the help of the wedge, or lifted with the help of the wedge, will remain in place for longer duration. And sometimes in our mundane life, wedges are driven at various places of a big weight or big object in order to hold that particular big object in a particular position, right? These are all the, and here in order to lift this heavy weight, a wedge is inserted, and of course a small force would be required. Therefore the wedges are typically called in our vernacular language as simple machines. Wedges are considered to be very simple machines because they require very less effort to do huge amount of work, huge magnitude of work. And when a wedge moves in this fashion, and there is a frictional resistance developed on this inclined surface, or the wedge surface or wedge interface, and exactly this frictional force which does the magic. And here is the normal reaction, and this is the resultant of the normal reaction and the frictional resistance. And this normal reaction, as we know earlier, that this resultant will be inclined at an angle of friction with respect to normal reaction. Here again there is a normal reaction offered by the floor, and this is the frictional resistance opposing the movement, and this is the resultant. Here again the angle born between these two forces happen to be the angle of friction, and here is the force. And this can be translated into a simple free body diagram. Here is the force P, which is just pushing the wedge in order to lift a huge block which is on the top of this particular wedge. And here is reaction R1. Reaction R1 is the reaction offered by the big block above the wedge towards the wedge, and this is the resultant reaction of this normal reaction as well as the frictional force offered by the floor to the wedge. Therefore in most of the friction problems, the free body diagram ends up in three forces which will keep the wedge or the block in equilibrium. Therefore Lami's theorem can be applied. Okay, wedge problems, typically speaking, is to analyze and to solve is very easy, though it looks little tough seemingly. And here we will go with the example 12, and till now thus far we have covered 11 examples, including friction problems on plane surfaces and friction problem on inclined surfaces. And here is the problem. A block is placed over the wedge. The block weighs 2000 Newton, and this is actually 2000 Newton. This particular block is 2000 Newton, a huge weight. Okay, this is 2000 Newton, and the question is, find the minimum force that is required to raise the block. Take mu equal to 0.3 for all contact surfaces. Wedge angle is 10 degree, and this is the wedge angle. So it provides some kind of an inclined surface in order to hold. And given F by N equal to 0.3 because mu equal to 0.3, and mu can also be taken as phi, which is tan phi equal to mu. Therefore phi equal to 0.3, and that will give us 16.7 as the angle of friction. Now the free body diagram of the top block is written, and here is the weight, that is 2000 Newton, and here is the frictional force which is opposing the upward movement. This is the frictional force offered by the vertical wall, and this is the normal reaction offered by the vertical wall, and the resultant of this normal reaction and the frictional force is R3. And here again this is the normal reaction to this inclined surface, and this is the frictional force. This is in opposite of the frictional force that is developed on the wedge, because wedge is moving inwards. Therefore wedge will experience a frictional force outwards, and here at the interface it is going like this, and the resultant of this friction force and the normal reaction happens to be R2. R2 will be inclined at an angle of friction, and this is the angle of the wedge, which comes as the inclination of the inclined plane, and with respect to vertical, this will also happen to be 10 degree. So therefore this though seemingly a complicated diagram is just translated into a 3-force system. This is the weight of the block, and this is R3, resultant reaction offered by the wall towards the block, and this is R2, it is the reaction offered by the wedge to the block. And the inclinations are mentioned. This is 16.7 plus 10, 26.7. And we can apply Lami's theorem because these 3 forces keep this particular block in equilibrium. Therefore R2, and R2 is very important for us to continue our solution process, and R3 is immaterial. R3 need not be found out. It is enough if you found out R2, because R2 will be translated, will be transformed in the reversal fashion over the wedge. So R2 by sine 90 minus R2 by this angle divided by this opposite angle. It is sine 90 minus 16.7, and 2000 divided by sine 133.4 degree. And if we recall Lami's theorem, the statement of the Lami's theorem is, if three forces acting concurrently at a point keep a system in equilibrium, keep a particle in equilibrium, then each force is proportional to sine of the angle between the other two forces. Okay, the same principle is applied, and R2 evaluates to be 2658.33 Newton. And we will just move to the wedge proper, and R2 is coming like this in a reversal fashion, and R2 was like this over here, and when it is translated or transformed over the wedge, it will come like this. Because, and if you just align the block against this wedge, and this one, that force will be cancelling away, and this should be read as the reaction offered by the block to the wedge. And this is inclined at an angle of, this is the normal reaction, and normal reaction is inclined at an angle of 10 degree. This is the angle of the incline, and this is the resultant. This is the angle of friction which the resultant of these two forces will make. And as far as friction is concerned, friction force will be going up, because the direction of the moment of the wedge is leftwards. This is the frictional resistance, and the direction of the moment of the wedge is like this. This is the moment of the wedge. Now this is written, and this is the normal reaction, and this is the frictional resistance offered by the floor to the wedge. Therefore the resultant comes like this, and this is the normal reaction, and the resultant makes an angle of friction. That is the definition of angle of friction, and this is force P. And now this can be simply transformed into a 3-force system. This is the reaction that just we calculated, and this is P, the force that is needed in order to push this wedge in order to hold the top block in equilibrium, and this is the bottom reaction. And we need P, and this is known force R2. Therefore we will make use of this known force in order to solve for P. So P over the angle is this. As far as P is concerned, we need to consider this angle. This angle happens to be 180 minus 26.7 minus 16.7. So 26.7 and 16.7 happens to be 43.4. So as far as R2 is concerned, this is the angle. This is the angle. Therefore R2 is 2658.33 divided by sine 106.7. 106.7 comes from the fact it is 90 here till here plus 16.7. So 90 plus 16.7 happens to be 106.7, and upon simplifying we will get the P, the force to be applied in order to just adjust this wedge in order to lift the block, is 1908.33. Now we'll go for the next problem, example number 13. If the weight of the block is 500 kilonewton, this block, find the minimum weight of the block B for motion to be impending for this particular block. Okay, now naturally this particular wedge has to move in the vertical direction, or initiating a kind of movement to the leftward direction as far as this block is concerned. And this is a supporting wall which is inclined at 70 degree, and mu equal to 0.2 for all inclined surfaces. Now we will immediately calculate the angle of friction, because it is required in order to draw free body diagrams and in order to align the forces, various forces acting concurrently. So therefore wedge problem mostly presents a concurrent force system. Therefore it can be said it is an application of concurrent force system in reality. So phi equal to 11.3, and this is the free body diagram of the block. This is 500 kilonewton acting vertically down. This is the normal reaction, and since this block is moving leftwards, there is a frictional force which is acting over here. This is the frictional force, and the frictional force and normal reaction will generate a resultant reaction over here, which is named as R3, and R3 is not required for us. Anyway, for the computational purposes. And then since this particular wedge is going downwards, it is going to experience the frictional force upwards, both here as well as here. Therefore, at the interface, the frictional force, which is equal to this, will be acting downwards, equal and opposite. And this is the normal reaction. Therefore, R2 will be going like this, and this inclination is nothing but 11.3, and same R3, same R2, sorry, it is R2, same R2 will be placed in reverse direction when we write the diagram of the free body diagram of the wedge that is shown over here, and this is the same R2. Okay, and for the sake of understanding, we can just lift this, and if we lift properly, R2 and R2 should be in this, it should be collinear, actually should be collinear, right? Anyway, we have the clarity of that. This is also F, and this is the normal reaction to this particular surface, and this inclines at an angle of 11.3 degree. This is angle of friction, and this is 20 degree. This is nothing but this has the inclination of 70 degree with respect to horizontal. Therefore the normal to this inclined surface should have 20 degree with respect to horizontal, and 70 degree with respect to vertical. And we translate this into this simple diagram. So this is just 11.3, yeah, and this is also 11.3, this is 11.3, and from this we have to, this is our starting point, because one force is known, all the angles are known. Therefore, with this we can calculate R2 applying Lamy's theorem, and we can further move to this particular diagram, and here R2 will become a known force, and with the help of known force and with the help of all the known angles, we can calculate W, the small weight that is required in order to just gently push the block of 500 kilonewton leftwards. That is the meaning of this particular, yeah, it has been separately written over here, and applying Lamy's theorem in the first instance for this particular block, 500 by sine 90, okay, this is 90, 500, and the angle between these two, it should be 90 plus 2 times 22.6, actually 22.6, it is being taken out. Okay, anyway, that is to be included. So R2 is not known to us, therefore R2 equal to 500 into this angle, the angular value, and here it becomes sine 90 plus 78.7. It becomes almost sine 90 plus 70.7 is almost 0.195, and here this denominator happens to be almost 1, because it is just sine 90 plus sine 102.6. okay, it comes to somewhere around 1 point something, okay, or 0.97 something like that. Therefore it is taken approximately as 1. So R2 happens to be 98 kilonewton. This is carried further in order to calculate the W, the question. So in order to calculate W, once again we apply Lamy's theorem. So W over 180 minus this and this, 32.6, 98 over, this is the reaction that is offered, this is the reaction offered by the block to the wedge, and this is the reaction offered by the wedge to the block. Therefore that is the directionality. So 98 divided by this angle, okay, 98 divided by this angle, 90 plus 21.3, 11.3. So therefore we will get W equal to 56.9. Right, we will go to question number 14. Another example. A block weighing 160 kilonewton is to be raised by means of 2 wedges, one here, one there, as shown. Find the value of P for impending upward movement of C, block C, to occur. Weight of wedges may be neglected mu equal to 0.25. So immediately we will calculate the angle of friction making use of this mu, coefficient of friction. It happens to be 14.03. And you should notice over here the system is very symmetrical, and here the reaction and the reaction will be equal. Therefore, if we take up the free body diagram of this and free body diagram of this, it is enough. And whatever the force that we calculate making use of half of the system will be simply applicable for this force also, for that P also. Okay, now we have written the free body diagram over here, and as far as the movement of this is concerned, it is going like this. As far as therefore there is a frictional force coming like this on this particular surface, and there is a normal reaction going over here. Therefore resultant makes an inclination like this. This is the angle phi. So angle phi happens to be 14.03. Therefore this becomes 16 plus 14.03, 30.03, and P is there. And here it is normal reaction acting vertically up, and the frictional force coming like this, okay, opposing the lateral movement of the wedge, and this is the resultant reaction, and we name this as R1. This as R1, yeah, this as R2, and R2 is immaterial over here. We need to find out R1 to further move. Okay, and we write the free body diagram of this. This is the resultant reaction which will be carried forward. This resultant reaction and this resultant reaction are collinear. So in the same manner there will be R1 coming from the other wedge, because the system is symmetrical. This is also R1. Okay, and we will translate this particular system block C into a 3-force system, and this is R1 and this is R1. The angle is 30.03 with respect to vertical, 30.03 with respect to this vertical, so that becomes 60.06. Now it is very easy for us to calculate R1. It is R1 over sine of this angle equal to 160 divided by sine of 60.06. Okay, we will do that applying Lami's theorem to block C. So 160 divided by sin 60.06 degree equal to R1 over sin 90 plus 90 minus 30.03. Okay, this is R1 over 90 plus 90 minus 30.03. This is the angle. Okay, that is added, and what we get is sin 150 degree almost. So R1 equal to 160 into this, cross multiply, and we will get sin 150 degree divided by sin 60.06 degree. It will fetch us R1 value to be equal to 92.32 kilonewton. Okay, and we will just continue with this, and we will apply the same R1 over this particular wedge, and any one wedge will suffice, and this is phi, and this is R2, and this is R1, which is known force for us, 92.32. Therefore we will write, and we will translate this particular system into a 3-force system. P is here, R1 is there, and R2 is there. So P over this angle, that is P over sine 180 minus 30.03 minus 14.03 equal to 92.32 by this angle. So it is 90 plus 14.03. So it has given us 66 kilonewton. So 66 kilonewton on either side is sufficient enough to adjust or to hold the big block weighing 160 kilonewton in position. Okay, that is the minimum force that is being required. And here is the last problem. A 15 degree wedge. This is 15 degree. This is also called as wedge angle. A 15 degree wedge is to be driven to tighten a body B, a block B, which is supporting a vertical load of 1000 Newton. This is a block B. A mu equal to 2.25 at all contact surfaces. Find the minimum force P required to drive the wedge. So you have to drive the wedge like this, and this will get tightened over here to the supporting support, let us say, and this is the bearing of the support. Anyway, and this is the free body diagram of the wedge P, and the direction of the movement of this wedge is like this. Therefore there is a frictional force going up. This is a normal reaction offered by the vertical wall. Therefore this is the resultant. Resultant is inclined with respect to normal reaction, normal force at an angle of friction, 14.03. And here this is the normal reaction over the wedge surface, inclined surface, and this is the frictional force going up because the direction is coming down, and this is the resultant. Resultant makes 14.03 with respect to the normal reaction, and it has normal reaction bears an angle of 15 degree with respect to horizontal. And this is because this inclined surface makes an angle of 75 degree with respect to horizontal over here. Yeah, and here with respect to this horizontal it makes 15 degree. So applying Lami's theorem for this, and this is the free body diagram of the block, and here there is a vertical force acting down, load, and this is R1 which is being translated over here, which is inclined at an angle of 29.03 degree, and this is the angle, the total angle, and this is the load that this particular block has to support, and this is reaction R2 which makes an angle of 14.03. So that is being translated over here. It's being translated over here. You look at the frictional force, because this block is moving this way. It's very important. Okay, it's moving this way, therefore this is the frictional force, this is a normal reaction, and this is the resultant reaction which inclines at an angle of friction, and this is R1, we have already stated this, and this is 1000 Newton, the load that is to be supported by this particular block. So this is simply translated into a 3-force system, R1, the load, and the reaction from the floor, from the support, of course. And we apply the Lami's theorem first for this, and we will get to know what the value of R1 is. Therefore R1 divided by this angle, 90 plus 75.97. Okay, this angle is 75.97. Therefore 90 plus 75.97 plus 1000 over this angle. Okay, this angle is 119, that is 90 plus 29.03, 119 plus 14.03. This total angle is this. Therefore we will calculate R1 to be 332.9 degree, and then sin 9 Newton. So we will continue with the known value of R1, and we will go back over here only to write the free body diagram of this, and it happens to be like this. The free body diagram happens to be like this: P and R2 and R1. R1 is known to us. R1 is the reaction exerted by the block towards the wedge. Therefore the directionality is shown like this. So 332, this is the reaction offered by the block to the wedge. Okay, when we wrote the free body diagram of the block, it is the reaction offered by the wedge to the block. It is something like that. Okay, they are mutually inclusive. Applying Lami's theorem to the wedge, once again we will write P is the unknown, P over sine 136.94, this angle, total angle, equal to 332, the known value of the reaction, divided by this angle, 90 plus 14.03, 104.3. So P happens to be 233.4 Newton. Therefore it requires to infer or to conclude, it requires a minimum of 233.4 Newton in order to push this wedge so that the block will be tightly aligned or tightly fixed with respect to the support. With this we complete our discussion on wedge friction, and if you liked this, kindly subscribe to my channel. Okay, and the next tutorial will be the friction analysis of friction with respect to ladders. Okay, and until then, bye.